In this video, I'm going to introduce and discuss electric resistance and Ohm's law. Electric resistance. So to describe electric force, electric potential energy, electric potential, even a current, I've been using the analogy with the gravitational potential energy, raindrops like water as an analogy. So let's see, when you have a water flow, when you have change in height. You have a change in height. That's when the water flows. If you just have a high altitude, but if there's no change, no drop, then water just don't flow. Only when you have a drop, then water flows. Same thing with the electric current, right? Electric current, when you have the potential difference, then current flow. Current flow. There's going to be a current that flows from high V to low V. And it has to be close, but typically though, and we're talking about conductive motion of a conductive electrons. So you connect some wire that's made of copper or something with a battery, right? You close the switch, current flows. So this is this wire. Inside this wire, there are conductive electrons, free electrons. Just like water in a water pipe, right? So these free electrons flows from high to low voltage. But this conductive wire, so was similar to this river. Like a river, depends on the river. There's some rocks in it. You're never going to have a perfect river that has no impedance. So these rocks in the river acts like an impedance. Or you can say resistance, right? This resistance, you can see it's there for the even in a conductive material, like a copper wire, for example, compared to steel. They're both conductors, but they're not perfect conductors. They're going to have some impedance in it. And for example, steel has more resistance. So the copper has less resistance. And this resistance, you have a resistance, and that depends on material. Like a copper and a steel has a different resistance. Also, the resistance depends on actually the geometry. And temperature. Mm. So resistance depends on the material. So you see that copper has less resistance than the steel. Geometry. Um, let's say imagine when you have a longer wire. So like the river, that's with the same density of rocks. So the same, it's made of same material, but you have to pass through longer distance. What would you think that it, do you think that it's easier to flow, for current to flow? Like the river that has the same density of impedance rocks and with a short river compared to the long river, which is easier to flow. You can see that a longer wire will have higher resistance. How about having a thick wire? So make the wire size to be thick, wider. Again, the density is the same. Density of impedance rocks are the same. But when you have when you make it thicker, you have more options to go. Although you're going to have a similar density of rocks, but that increases an option to go that way or this way or this way. It's almost like a similar idea as that you're waiting for a cashier. Maybe you are at Target on the Christmas time that, you know, you only have a two cashiers available versus 10 cashiers available. So of course you want to go with the case that 10 cashiers available, right? So having a thicker wire or wider wire gives more options to flow. So you actually have a lower resistance with the same material. This is uh, um, increasing temperature. So let's say if you increase in temperature, that's like almost like those rocks in a river. If you increase in temperature, they can move around with the bigger. So the size of the rock itself might be this much, but if they move around more, that's going to cause more impedance in a for current flow. So increasing temperature means um, increase in resistance. So resistance of the for the current flow in a conductive wires depends on or electronic device depends on the type of material that the electrons are flowing, depends on the geometry, and depends on the temperature. And varying these factors, the resistance do change. And here Electric resistance. We typically use R for the electric resistance. And we use the unit. This is a Greek omega. And we use this is called ohm. So unit for the resistance, we can say 10 ohms, 1 kilo ohm, that kind of a thing, to show the resistance. Here, this is the very useful law that's called Ohm's law. It's not a fundamental law. This is an empirical law. So Ohm's law is not like a Newton's law of motion. That's not that fundamental. But it's very, very useful. It works for most of the time. So we use it. What Ohm's law say is current flow is equals to voltage divided by resistance. I is equals to, I want to make sure you write this, change in voltage drop versus divided by resistance R, right? So 1 ampere is equals to 1 volt per ohm. And again, I'm emphasizing this is the voltage drop, right? Constant voltage, if you say 20 volts, but it has to be the 20 volts difference. It's the voltage difference. If it's just the 20 volts, that no change, then you're not going to have a current flow. So, but bigger the potential drop, bigger the current. Bigger the resistance, less the current. Makes sense. So you can use the Ohm's law to find the relationship between a current and voltage and resistance in electronic device. There are some materials that do not obey. Just in case, some materials do not obey Ohm's law. And these some of the materials that do not obey Ohm's law is called non-ohmic. So you see that there are some materials that do not obey, but typically they follow this Ohm's law. Bigger the potential, bigger the resistance, current, and then the bigger the resistance, less the current. All right, so this is the end of this video, and I'll see you in the class.